Ladies and gentlemen, tonight we're going on a fantastic journey. And taking us on this journey will be scientists at the Weizmann Institute. Mankind's quest for new knowledge is as old as our species, and sometimes you have to marvel at how we got here. Ever since mankind organized himself into communities and collectives, villages, cities, societies, our curiosity and urge to discover has grown and grown, and now in the 21st century, we are looking to the stars for our next great voyage. And I should know.
Captain Kirk should know. He's the one who told us that space is the final frontier. And now, here we are, launching one of the most exciting initiatives underway on the Weizmann Institute campus, the flagship project called Frontiers of the Universe. Before I go on, I would like to invite you to send in questions by chat mode, which will be made available at the end of the session. We will try to answer as many questions as we have time for during the Q&A with all of our presenters. The Frontiers Initiative will explore the physics of our natural world as it occurs over infinitely small distances, like the space between atoms, and at the grandest scope, the space between stars. This integrative approach is the road to understanding everything that makes up our world, from the tiniest subatomic particles to the largest galaxies, to the very existence of space, time, and life itself. Building on important discoveries that have made Weizmann scientists leaders in the astrophysics and particle physics communities, and creating the basis for a new center for space missions like UltraSat, the Frontiers of the Universe initiative is propelling the Weizmann Institute to the very forefront of the world science community. To a physicist, there is nothing more exciting than exploring the universe. If that is, we cannot be in space ourselves. But why should I talk about it when I can show you? Follow me. Hey, Sagi, what are you doing?
I'm looking at star velocities in dwarf galaxies. I've done these calculations 100 times. I can't get them to make sense.
Let me take a look. According to this, there needs to be at least 100 times more mass, more stars at the center of the galaxy in order to keep the stars at the edges from floating away. Something is missing.
I couldn't help overhearing. I'll tell you what's missing. There's a certain mass in the center of those galaxies that we cannot see. This mass is holding everything together, and we call it dark matter.
Let me explain. The discrepancy comes from the difference between the visible mass and the star velocities. Just like what happens when you pick up your kid and swing them around, going around faster and faster. It flings Junior out, while the forces of your arms holds him in, which saves us several trips to the hospital. We can measure how fast the galaxy is going around itself. It's pretty damn fast. And the stars in the arms, on the outskirts of the galaxy, should be flung out, since the force of gravity in the center is not enough to hold them. Just like Junior would if your arms were too weak. I'll explain using another example everyone knows. The Earth revolves around the Sun at around 30 kilometers per second. The reason it doesn't fly out of orbit is that the Sun's gravity holds it in. And that all makes perfect sense. But at the galaxy level, mass is missing. That's the mass we call dark matter. In fact, the first person to notice that was Professor Vera Rubin, exactly 50 years ago. And they are now naming an observatory after her, a large one being built right now in Chile.
Interesting. Seems like there is a lot we can learn from rotating objects. We use the rotation and velocity of exoplanets around their suns to see them and learn about them.
Exoplanets? Tell us more.
Exoplanets are planets that orbit around other stars, and we know today that most of the stars in our galaxy host such exoplanets. We cannot see planets directly in distant solar systems, but we can learn that they are there by looking at their light coming from the star. It is the rotation of the planet around the sun that gives us this information. Just as the gravity of the star causes the planet to move, the gravity of the planet causes the star to move. The star rotation induces a Doppler shift on the light emitted from the stars, which we can measure, thus detecting the planet. Sometimes we are lucky enough that the planet passes in front of the star and hides some of its light. This is a pretty big hint. The first exoplanet was discovered only in 1995 using exactly the Doppler shift method. The two scientists leading this effort won the Nobel Prize in Physics in 2019. We know today of roughly 5,000 exoplanets which have been detected by various methods. Some planetary systems are similar to our own solar system, with terrestrial planets like Earth and Mars closer to the star, the Sun in our case, and gas giants like Jupiter and Saturn further out. Some, however, are very different, like a super-Earth in this NASA tourist poster of the exoplanets HD 40307G with a radius more than 2 times that of Earth. Or even a planet orbiting 2 suns, where your shadow always has company. Perhaps some of you heard of such planets. It's not just science fiction.
Luke knows what I'm talking about.
We need special equipment to detect these planets, and so we are now building a unique observatory in the Negev equipped with 48 wide field of view telescopes. Each telescope will be equipped with a unique fast camera that will allow us to detect planets in orbit around significantly smaller hosts, such as white dwarfs, the last stage in the life of a star like our Sun. The first such planet was detected less than a year ago, and the planet detected is much larger than the host star. Pretty cool.
Dwarf stars? Twin suns? Rotating galaxies? I'm getting dizzy. Let's go back to the ground.
Hey Sagi, what are you doing here on the ground?
I'm looking for the dark matter.
But that's not how you look for dark matter. In fact, you can't even see it.
Remember I said dark matter was first detected by its influence on gravity? That's because it flows through everything, even us. It can, however, collide with us, or with a detector if we build it the right way. It would leave a tiny trace, but we're getting pretty good at finding these tiny traces. But the universe is full of all kinds of radiation. In order to not be overwhelmed and blinded by the other radiation, we must go underground, which is why my lab is under a mountain. We built a long tunnel. It's a very long tunnel, really long. When I say long, I'm talking long. Total length is 10 kilometers. Once we get to the lab, we have a giant bucket filled with extremely pure liquefied xenon, with light sensors above and below. Xenon is just an awesome material for these experiments. When a particle passes through and hits an xenon atom, this atom will deposit its energy and give first signal of light. Tiny, but we can find it. At the same time, some electrons are freed, and they drift up to the top of the xenon bucket. They do that because of the high voltage we put across the structure. Once the electrons are at the top, they emit a second flash of light. This might not sound like a lot, but with that light, we can say so much about what happened. What kind of particle that was, where it hit, when it hit, how much energy it deposited. All we have to do now is figure out that these do not come from some old and boring type of radiation. And there you have it, dark matter. Well, maybe it's not that easy, since the experiment has been going on for 4 years and no dark matter yet. But we did discover pretty cool things meanwhile. For instance, we found an atom that decayed from Xenon 124, something that takes about 1.8 sextillion years to happen. That's not a made-up number. It's about 130 billion times longer than the lifespan of the entire universe. So we know our detector is really, really sensitive. And all that with just 2 tiny flashes of UV light.
Ronnie uses UV photons to discover dark matter. We also want to use UV to discover interesting things, but in space. So we have decided that time has come to go up to space. It's just the first of the Weizmann-led Israeli scientific space missions, called UltraSat. It's one of the biggest projects we've ever taken on, and it is the project that is going to allow Sagi to follow his heart's desire.
What I really want to do is look at the exoplanets that most resemble our own Earth. These planets might even have a biosphere similar to that of Earth. For the first time in human history, we can try to answer scientifically how much life is abundant in the universe. When observing Earth from outer space, oxygen is a strong indicator for life on our planet. Without life, our atmosphere would not have such a high concentration of oxygen. So that could be true for other planets as well. If we detect oxygen in a planet's atmosphere, we have a strong indication to a possible thriving biosphere. But the ultraviolet emission from the host star will influence the O2 levels in an atmosphere, as well as the generation of a protective ozone layer. UV is also the only known energy source we know of that can explain the generation of the messenger RNA, a precursor to DNA, on our own planet, an essential step in the evolution of life on Earth. Understanding the UV emission from various stars is essential to understanding the evolution and prevalence of life in the universe. The UltraSat space mission will have unique capabilities, allowing us to achieve unprecedented understanding of the UV emission from stellar objects. UltraSat data will tell us what type of stars are more likely to host an habitable planet and guide our studies of planetary systems for many years to come.
At the Weizmann Institute of Science, we have a tradition that all buildings are started and are finished at the International Board. Apparently, this is true also for space launching. This year, let's take a little journey into the future to 2024.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, lift off.
Did you ever wonder what we're made of? We're all stardust. The elements that compose us are actually forged in huge cosmic explosions in outer space. In understanding these cosmic explosions, you have to actually look at them at the very second they ignite. And that's something you can't do with ground-based telescopes. If you want to do that, you have to take your telescopes, put them on satellites, and launch them into outer space. And that's exactly what we're going to do.
UltraSat became a project way back in 2019, but the truth is that we've started thinking about it already in 2010, trying to find ways to answer some of the big questions in astrophysics using Israeli technology.
The main motivations of UltraSat are transient astronomy. Transient events are rare events. You can't just wait and on a very small region in the sky and hope that you will have that event happening there. So you need to monitor a large fraction of the sky, so the probability of having those transient events are large.
For UltraSat, this was probably one of the biggest challenges, to find an optical design that is capable of providing both the very wide field of view and reasonable image quality.
There are signatures that you can see in the UV light curves that you cannot see in other wavebands, but you must go to space in order to observe in the UV, because UV is not penetrating in the atmosphere.
Specifically, it tells us something about very hot objects in the universe of temperatures above tens of thousands of Kelvin, which is usually the setup in cosmic explosions like supernovae.
By studying these objects, we hope to answer some of the big open questions in astrophysics and in physics in general, like how black holes grow and affect their environment, how stars explode, where in the universe the heavy elements were produced, and which stars are most likely to host habitable planets.
You look at a phenomenon and you say, according to all my theoretical understanding and my previous experience, this thing should not exist. And yet, it exists. And that's what really drives our knowledge forward, finding the thing that you didn't expect, that you didn't predict, and you cannot explain, at least initially. Because we are taking data that nobody's taken before. Nobody's looked at such images. You know, nobody has these big UV cameras in space. You just cannot take this data any other way.
One of the unique aspects of UltraSat is that it is the first major project in which the industry and the academy are collaborating so closely and on such a large scale.
Weizmann Institute approached us to support them. It is the biggest astrophysics mission that we are doing now.
UltraSat drew major research institutes and agencies to combine and partner with us in this project. Spacecraft itself that carries the telescope was produced by the Israeli aerospace industries. The telescope was produced by ELOP, which is across the fence from the Weizmann Institute. The camera that sits at the heart of the telescope was constructed by our German DESI partners, which is the leading institute in Germany building hardware for particle physics experiments. And at the center of this camera sits a sensor which was produced in Migdal HaEmek by Tower Jazz, another Israeli company.
The image is stored as a file on the satellite computer, and the data center is now the brain behind all of this. So these images are coming in, and you have to analyze them very rapidly, because remember, in a couple of minutes there's going to be a new image. You cannot have any backlog. There's going to be no rest. So in the data, we have to quickly separate the information, the astrophysically interesting stuff, from noise.
UltraSat is a discovery mission. Its sole intent is to find new targets and then to transmit it to the ground, and from the ground we will trigger all the other telescopes necessary to follow up in the optical, in the X-ray, in radio, to take spectrum.
It's quite a responsible job because there's action being taken based on your data. So this action might be a big telescope somewhere that is very busy doing somebody else's science. And now, because something happened over there, they stop doing that science and they start doing our science looking there. And sometimes these are even other space missions that are turning around.
There are questions that you can answer by yourself with your own telescope, but many of the answers you must have these coordinated observations.
One of the things that UltraSat accomplished was to strengthen Israel's international standing. NASA has chosen to join UltraSat under Israeli leadership to provide the launch for this mission.
Since space is a high-profile program, nations tend to collaborate in space. Definitely doing a collaboration with NASA have a political meaning.
The whole goal of the space agency is to take whatever was created here in Israel for security, to transfer it into normal civilian, scientific, commercial applications.
I am certain that a scientific project of the scale of UltraSat would have a sort of an Apollo effect in Israel, drawing talented young Israeli students to science and technology, which is crucial for Israel in general.
It's great exposure for our industries that have been such good partners to us. I'm sure it's going to bring more business to them and the people they employ. It's very good for our space agency that really puts itself in the front as a leading space agency.
We are in a competition. We know that we don't know all our competitions and what are their timeline, but we know that we're ahead of them and we want to keep that.
For all the donors and friends of the Weizmann Institute who are partnering with us on this exciting journey, if you ask yourself, how can you make real impact on the ability of the Weizmann Institute to perform cutting-edge research, I think this is probably a singular opportunity to advance us as an institute to a whole new level. There are very few institutes in the world who have a space research program. This puts us at this very unique and exclusive category that would be a game changer. So we would like to invite you to join us on this really frontier-breaking journey together with us.
Thank you, Ronnie and Sagi, for taking us along on your virtual journey to the edges of the universe.